Ever wonder how AI gets so good at solving math problems or writing code? It's not just about memorizing answers, it's about reasoning. And a new breakthrough in AI research is showing how combining two powerful techniques can take this reasoning to the next level. Let's break it down. Imagine teaching a robot to solve puzzles. First, you give it lots of examples. This is called Supervised Fine-Tuning, SFT. Think of it as a tutor guiding a student through step-by-step solutions. But then, you want the robot to figure things out on its own. That's where reinforcement learning, RL, comes in. It's like letting the robot try different strategies, rewarding it when it succeeds and nudging it when it fails. But here's the twist. Researchers found that combining SFT and RL isn't just additive, it's exponential. In their study, they tested how scaling up SFT data, more prompts, more answers per prompt, improved performance. They discovered that increasing the number of prompts had a bigger impact than generating more responses. It's like practicing with a wider variety of problems, rather than repeating the same ones. Then came the real game changer, pairing SFT with RL. They asked, how do we balance exploration, trying new approaches, and exploitation using what works? Their answer: a clever trick with temperature settings. Think of it as adjusting the robot's curiosity. Too high and it gets lost, too low and it's stuck in old habits. They found that keeping the temperature around 0.3 struck the perfect balance, letting the AI explore just enough to improve without chaos. The result? Their model, AceReason-Nemotron 1.1, smashed previous records on tough math and code benchmarks. It's not just faster, it's smarter, solving problems that even its predecessor, AceReason-Nemotron 1, couldn't crack. And here's the kicker: the better the initial SFT training, the more the RL could refine it. It's like giving a student a solid foundation, and then letting them tackle harder challenges with feedback. So why does this matter? As AI takes on more complex tasks, from coding to scientific research, these techniques could make the difference between a smart AI and a truly capable one. The next time you see an AI solving a tricky math problem, remember, it's not magic. It's a mix of practice, feedback, and a little bit of calculated curiosity. Let's dive deeper into the experiments. Researchers tested how RL transforms SFT-trained models. They used a metric called pass at K. Imagine a quiz where you get points if any of your answers are correct, even if others are wrong. The higher the K, the more tries you get. This metric shows how reliably a model can solve a problem, not just once, but consistently. On coding challenges like LiveCodeBench, RL-enhanced models solved over 10 more tricky problems than their SFT-only counterparts. Even when the original SFT model struggled, like when it had less than 20% accuracy, RL helped it catch up. It's like giving a struggling student targeted tutoring. The more they need it, the more they gain. But the biggest surprise: RL didn't just improve math or coding skills, it created models that could tackle harder problems overall. On math benchmarks like AIME, a tough competition for AI, RL models kept improving even when generating 128 possible answers. However, for math problems with limited answer choices, like small numbers, the gains leveled off. This tells us RL is especially powerful when creativity and precision matter, like writing code or solving open-ended problems. So what does this mean for the future of AI? It shows that even when models start strong, RL can push them further, especially in areas where trial and error is key. Whether it's cracking complex equations or writing flawless code, these techniques are helping AI reach new heights. Want to explore how this works in practice? We'll break down the experiments, the math, and what this means for the future of AI right here on this channel. Hit subscribe, and let's explore the mind of the machine together.